in essence is the number of charges or volume. Number of mobile charges, I should say. Because if I have an atom, I've got a whole bunch of charges in there. Wherever, oh, got stuck over there. So, I mean, especially on the lower part of the periodic table, I got a whole bunch of charges. What really matters here is how many electrons are actually free to move. Because not all the electrons in an atom can easily move. Those are not really considered mobile charges, I guess, unless you crank the voltage up. So I need to know the number of particles that are traveling. I feel like there's a letter missing there. All right. I know current is the charge passing by a particular point at a particular moment in time. So if I have n charges going through over a certain amount of time, n charges times the charge of them. I know n, the number of charges that would be flowing past it, will be equal to my charge carrier density times my volume. So this becomes the charge of what's flowing, which is, let's face it, it's an electron, times n capital V over T. The volume, if I'm in some amount of time here, I'm going to have, how far will these charges actually travel? Well, they're going to travel its drift speed times however much time we're talking about. And so the volume of this region here, about the number of charges that will pass by, we'll just say that will reach here, will be, well, that distance times whatever the cross-sectional area is. Think of it as I got a cylinder here. A charge is passing through the cylinder, and so the volume of that cylinder is just going to be the area, cross-sectional area. This A is for area. I'm not sure writing it actually helped because I'm not sure how legible that is, but this is cross-sectional area times VDT over T.
Is that a continuation
Of this up here. I know my drift speed, we calculated that right there. And so my current would be charge of the electron times the mobile charge carrier density times the cross-sectional area times charge of an electron times the electric field over mass times tau. So just taking this right here and plug it in for Vd. Which simplified, I have E squared, so charge of an electron squared, N A E tau over M. Really not much simpler. We combine the E's, the little E's. Well, if we think about this a little bit more, some of these are constant. The charge of an electron is constant, as far as we know. That's a constant. The charge carrier density here is, mass of the electron is constant, so those are constants. The charge carrier density and tau are material dependent. So I could just take those four objects right there and go, well, if I know what the material is, I could tell you what all that stuff is. Well, I know those two without having to know the material, but the other two I could look up. So why don't we just create a material dependent variable? So why don't I'll use sigma and let that be equal to E squared N tau over M. It's just a constant times these two things that are dependent upon the material. And this is known as conductivity. So I've now taken all of that and I've broken it down to that the current is going to be equal to this conductivity times A times E. A is the cross-sectional area of the wire. E is the electric field strength. Questions up to here? We're more than halfway through of this derivation.
The E is energy field, right?
No. The electric field strength. If that makes it clear. It is not energy.
Okay.
So if I have a wire though, and I hook it up to a battery, I'm really not gonna be able to, I don't know what the electric field is. I mean, the exercise that you did yesterday, in the lab you did yesterday, we couldn't measure the electric field. We had to measure the electric potential and, from that, figure out at least the direction of the electric field. But if we make the assumption that the electric field is constant through this wire, it's a decent enough assumption. What is the relationship with the electric field and the potential difference? And we faced this with the parallel plate capacitor because the electric field in between it we assume was constant. So if the electric field strength is constant, what is the relationship between the electric field and the potential difference or voltage? Someone's about to reveal this to you. In past lifetimes, or sometimes referred to it as the Ed equation.
What was the question?
If the electric field is constant, which we are assuming, which is a decent assumption, what is the relationship between this and the voltage?
Delta V is equal to negative E D.
Is it ED? Yeah. Or thus the Ed equation. D is the distance that it's traveling through. With parallel plates, the lowercase d often is the distance between the plates. The negative there means that, if you recall here, we had the high side over here, the low side over there for potential. So if I'm going from high to low, my change in potential is negative. The electric field is going in the same direction. So if I just did E dot delta X, I'd get a positive number, and I would need the negative to balance them out. In essence, the electric field goes from high potential to the low potential. That's why there's a minus sign there. So this equation up here now becomes sigma A delta V over how far the electrons are moving. In essence, or strike that. If I have my wire here, I have my battery here. This is where my potential, this is my high potential, this is my low potential. It's creating this electric field going around like that. So it's how long the wire is. Or I guess the distance between between the two potentials that we know. That's still worded badly. It is the distance between the 2 points for which we know the potential difference. That's more accurate, although potentially more confusing. In the case of a battery hooked up to a wire, it's the length of the wire.
I have a question,
Yes.
and maybe I'm just getting confused.
My explanation has been flawless. So, anyway.
I'm thinking about the distance D, and I'm thinking about relation to change of position with respect to the origin unit displacement, which is delta S as a vector, right?
Yeah, you said one thing in there that,
It's probably wrong. Well, I guess with respect to the starting point?
yes, okay.
Okay, so I guess my question is, I guess I'm not understanding why it's displacement, because I thought displacement, I don't know.
Okay,
My brain's having a hard time, cause like, you know, if you're like, I need to get from here to here, and the actual path it goes is like this, but we're like, oh, but how far apart are those 2 points?
okay, so,
2 steps.
all right, so you're thinking, looking at this and going, it's not very far.
Yeah. When I'm thinking in terms of like
Yeah,
displacement.
no, I understand that. I actually have an explanation for it.
Okay.
All right, I have 2 points right here. I have a particle moving from there to there. I have some particle moving from this spot to that spot, and I have an electric field traveling in the same direction. I know from this, if this particle started at rest, that it must be a positively charged particle because it's going with the electric field. There's a potential difference between that. The potential difference between those 2 points is going to be the negative of the electric field dot delta x. And so delta x would be a vector in that same direction. So that you just multiply E times delta x, you're good to go. If I had a point here and here, if my electric field is going to the right again, and this time the particle is moving like that, well, part of the movement is perpendicular to the electric field, so I really don't care about that. I only care about the part in the same direction as the electric field. So what I would do is I would really look at
Just that.
the amount that is in the same direction when I multiply. If I have a wire here, which basically limits what path the electrons can go in the electric field, it's sort of like a fiber optic cable, sort of keeping things inside. My electric field is going this way, that way, that way, that way, and that way. My electric field is not in a straight line. It is, assuming that the magnitude is constant, but the direction actually changes, opposite direction of the electron actually flowing. So throughout the whole thing, so in this segment, they're anti-parallel, and that segment, they're anti-parallel, same there, there, and there. So you're really doing a sum of all the different segments.
Okay, that makes more sense.
Okay.
Thank you.
Yep. Any other questions? I know, you're excited to get to the end. What's gonna be revealed? So I now have my current is equal to sigma A delta V over L. Just rewriting what I have over there. This is material dependent, known as the conductivity. You can look it up if you, conductivity of aluminum, conductivity of copper, you can just look it up. Cross-sectional area of the wire, difference in potential, or potential difference, and the length of the wire. So what I'm gonna do is, I'm just gonna solve for delta V. Because traditionally, it's solve for delta V. So if I solve for delta V, that means I've got the length of the wire over my material constant over the cross-sectional area of the wire times the current. Ooh. And then physicists, for whatever reason, said, you know what? Let's think about what this actually means. Let's say I got a 12 volt battery and I got a 100 volt battery connected to a wire. Which one's gonna produce more current? If it's the same wire. Got a 100 volt battery and a 10 volt battery.
100 volt.
Yeah, if it's the same wire, the same. But if I made the wire even smaller though, but if I went with, I got a 100 volt battery, yeah, I'm gonna produce more than a 10 volt battery, but if this is 100 volts here, I could limit the amount of current flowing through there by just changing the cross-sectional area of the length of the wire. If I got more wire, there's more chance to run into things. If I make the wire skinnier, there's more chance to run into things. There's less wiggle room. I can't really, there are fewer, it's like trying to get from that corner of the room to that corner of the room. If I made a very narrow passage with tables in the way, it's gonna be a lot harder than if I made the room twice as big, kept the same number of tables. You know, there are a lot more ways to get through. So they said that this really is a measure of how hard it is for the particles to move. The harder it is to move, the smaller the current's gonna be. The easier it is to move, the more current I'm gonna have flowing through. So this really deals with a resistance of some sort, but it doesn't really make sense to somebody that we use this concept called a conductivity when we're talking about resistance. So they came up with a brilliant idea of, let's define this thing called resistivity. The symbol for resistivity is the rho. It's the same symbol used for density. And they're just going to say that is 1 over the conductivity. At one point I thought, surely it's not, why didn't it just keep the sigma in there instead of creating a whole new variable? And if you look up, I've seen tables of resistivity and conductivity of materials, and they're just reciprocals of each other. There was nothing special else in there. So this now becomes the resistivity times the length over the area times the current. And then they got this right here, and they said, you know what? Wow, that's just so much to write. Why don't we just call this resistance? And the symbol for resistance is a capital R. Probably from the French. Resistance. And so this formula is more traditionally written as the potential difference is equal to the current times the resistance. This is known as Ohm's law. That is probably the most important equation up here. However, this equation, the fact that the resistance equals rho L over A, we will do a lab on that. We will take various lengths. We'll measure the cross-sectional diameter from using a micrometer. From that, we'll calculate the cross-sectional area. And we have the cross-sectional area. And we know the length. We'll measure the resistance. And we'll calculate rho. It's slightly more complicated than that, but that's the essence of it. And then we'll compare it to what the book value is. Do keep in mind, we still have only had one physics equation, Coulomb's law. This is just Coulomb's law, except with a couple of definitions in math. But Coulomb's law, it's in there, it's the heart of this. Take a wire, diameter, so it's a cylindrical wire, diameter of 21 microns. Let's make this a length of 50 meters. And we'll make it copper. Because I think I have the copper values here. Okay. What is the resistance of this wire? Well, I know that's equal to rho L over A. Rho, that is